Greetings everyone, I'm Elizabeth Hutchens and this is my final project report for Geography 481. My final project is a watershed model for potential flooding locations for a military training location named Hickory Landing, located approximately 36 kilometers from Shaw Air Force Base, Sumter, South Carolina. The training area expands approximately 1.72 square kilometers. A watershed is all the land that drains into the same locations or body of water. People tend to think only of water bodies such as rivers, lakes, and wetlands as being part of the watershed. However, any land, whether it is parks, farms, forests, school parking lots, even soils we build our homes on, is also included. Think of a watershed as a funnel collecting all the water within a specific area and draining into the nearest body of water, making its way to larger rivers and eventually the ocean. Understanding the mechanism of a watershed can help identify potential flooding locations for training and planning purposes. In this presentation, I will discuss the original idea, the data used, the data processing methodology, discuss the results, expected or unexpected, and share my lessons learned. The original idea for this final project was to create a how-to guide for my section. After a request for information was submitted, it became extremely apparent that no one in my shop knew how to properly perform a watershed analysis, including myself. After asking additional questions on what type of data can be used to run the process, I also noticed that my team did not fully understand LiDAR point cloud data, so I wanted to include that into my how-to guide. So, because the request for information was submitted on a classified location, I decided to recreate the request in a local area known as Hickory Landing Zone, located approximately 36 kilometers from Shaw Air Force Base, Sumter, South Carolina. The original idea for this project was to create a workflow for converting the LiDAR LAS dataset to bare Earth digital elevation model and perform a watershed using the hydrology tools in ArcGIS Pro, and to investigate any potential flooding locations at a military training area that will be used to build a training building on Hickory Landing. The detailed workflow original idea is depicted on the right. The LiDAR data workflow included downloading the LAS point cloud data and turning it into an LAS dataset that can then be turned into a raster DEM, which would then be used in the geoprocessing of a watershed workflow. The hydraulic processing is to extract hydrology information from the created DEM of our study area. The hydrology tools are used to derive several data sets that collectively describe the drainage patterns of the basin. Geoprocessing analysis is performed to fill the sinks and generate data on the flow directions, flow accumulations, stream to determine pour points, and then to run a watershed tool. The data for this project was downloaded from Open Topography. The one-tile LiDAR dataset was USGS LPC SC East Central 2017 LAS 2019. The LiDAR file was LAS V1.2. The horizontal coordinate system was NAD 83 UTM Zone 17 North. The vertical coordinate system was NAD Vid 88. The spatial resolution was in 1 meter. In this project, the data processing methodology for converting LAS files to a DEM is processed and analyzed to include only ground points. This is a very important step, and if other codes are selected, the DEM will include those points other than bare earth, and the process will take longer. Point cloud data obtained from LiDAR presents elevations of various landscape features. The features are classified into codes. Various digital elevation models can be produced from this data. But since we are going to be performing a hydrologic analysis on this dam, the ground classification code was the only code used to generate the bare earth dam. In this project, the data processing methodology for the hydrologic process is to extract hydraulic information from the created dam of our study area. The hydrology tools are used to derive several data sets that collectively describe the drainage patterns of the basin. Geoprocessing analysis is performed to fill sinks and to generate data on the flow direction, flow accumulation, streams, stream segments to determine pour point, and to produce the watershed delineation. The results from the analysis can be seen in this slide. Understanding the role and mechanism behind a watershed can help identify any potential flooding areas within the training area. The watershed here is comprised of a number of streams and creeks that drain to a progressively larger area. Each of these streams and creeks have their own watershed or subbasin that flow from higher elevation to lower elevation. Considering that this is the first time that I have ever done a process like this or analysis like this, my biggest lesson learned was understanding the process of determining a pour point. I felt as if this was one of my difficult tasks. After further researching, I realized that this can be done several ways. One, just by zooming into the location of a stream and creating a point based off that, then running the watershed analysis tool. There are other mechanisms that run a stream definition tool before running a watershed pool. Overall, this was my biggest hurdle during this project, but it did give me a better understanding of what a pour point was. My second lessons learned was to double check the LAS dataset to raster process. When I first ran this tool, it looked like it did not remove all the classification codes, so I had to run the process again. Overall, since this was my first time actually doing an analysis like this, I think conducting this project helped me have a better understanding of what a watershed model is and also have a better understanding of the LiDAR processes to turn LAS dataset into a raster. In conclusion, the original idea for this final project was to create a how-to guide for my section. After a request for information was submitted, it became apparent that no one in my shop knew how to perform a watershed analysis. After asking additional questions on what type of data can be used to run the process, I also noticed that my team did not fully understand LiDAR point cloud, so I wanted to include that into my how-to guide. This project really helped me create the baseline for my how-to guide, especially including any hiccups, concerns, or any bumps in the process that I've encountered. This project was to create a workflow for converting the LiDAR LAS data to bare earth digital elevation model and perform a watershed delineation using hydrology tools in ArcGIS Pro and investigate any potential flooding locations at the military training site Hickory Landing that was chosen because the original request was a classified location. I decided to recreate the request in a local area known as Hickory Landing. This project really helped me have a better understanding of how to process LiDAR and also how to use the hydrology tools. It gave me confidence in processing LiDAR data and understanding those hydrology tools. This concludes my final project report. If you have any questions, comments, or concerns, any feedback, please feel free to let me know. I hope you enjoyed my my presentation, and thank you for tuning in.